So I must say I'm also very sorry for not being there due to family constraints, but I nevertheless enjoy very much the talks that I've seen so far online and also on YouTube. I would like to thank the organizers for this opportunity to present this recent work here. Let me, of course, share my screen. And yeah, so I'm going to talk about a recent work that is currently in preparation. Most of the work has been done by this gentleman right here, who is a postdoc in Loughborough right now. And also this was done in collaboration with Joseph, who is also in Loughborough. The story is basically the following, is that we start with a highly frustrated magnet, such as the planar pyrochlore or the checkerboard lattice, and which is known to have infinite competing orders. And then we switch on some, yeah.
So can you make it full screen mode?
Yes. How about now?
Yes, sir. Fine. Thank you.
Good. And then we will turn on chiral perturbations. The most natural one is the Dzyalozinskii-Moriya interactions, which we will take a minimal model that will as a playground. And then we are going to ask what kind of phases do we expect in light of the fact that we have a lot of competing orders, and in addition that we break inversion symmetry by the Dzyalozinskii-Moriya interactions. And we're going to argue that there is interesting novel incommensurate phases that can arise as a result of this combination. This work was supported by the Engineering and Physical Sciences Research Council of the UK. And okay, so I thought about the structure of the talk, and I decided to give to spend some time on providing, let's say, a general phenomenology of the kind of concepts that we're going to be talking about. So I'm going to start by from the beginning by talking about the distinction between localized versus extended kind of modulations of order parameter fields. I'm going to talk about Lifshitz invariants, which seem to play a very important role in some of these phases. And then I'm going to give you some selected examples from my own research in the last years. And then I'm going to move on to the main topic of the talk, which is the impact of Dzyalozinskii-Moriya interactions in a system that has already not one, but multiple competing orders. And then I will conclude. Okay, so let's begin. Okay, so let's start with order parameter fields. So we start with, let's say, the standard example of a Heisenberg ferromagnet, and draw the ground state or one of the ground states. We know that this breaks rotational symmetry, and it's described by a local order parameter M, which is uniform in the ground state. Then there is the excitations, which are described by modulations of M in space. And then there's a distinction between extended modulations, Magnon-like, which we know cost zero energy only in the limit of infinite wavelength, versus localized modulations. And here I draw two very standard examples: the XY vortices, skimions, which we have already heard about in this conference, and then also Z2 vortices that I'm going to discuss also in this talk. Okay, the question is, can these kind of excitations or like localized objects not be just excitations, but really exist in the ground state at thermodynamic equilibrium? And we know historically there is a lot of prime examples of this concept. And one is the vortex lines in type 2 superconductors, and more recently the skimion crystals that have been seen in many chiral helimagnets. Okay, so what is the main physical mechanism is that we have a Hamiltonian, we have a dominant energy part, which typically favors a uniform order parameter. That order parameter can be a vector, can be a tensor, or whatever. And then we switch on a perturbation that is there in the material, for example, anisotropy, and that perturbation favors a twisting of the order parameter. And there are two ways to accommodate this kind of twist. One is the linear way or the harmonic way, where the order parameter twists in a linear way as a function of the distance. And there is also the nonlinear way, which is anything in between, where you take basically different versions of the parent commensurate phase here, a domain with upspin separated by a domain of downspins, and then you put in between so-called discommensurations, which are what we call now localized or particle-like modulations of the order parameter that typically cost energy, but here, because there is this interaction V, that gives a negative energy contribution. And the period between these discommensurations goes to infinity when we switch off the perturbation. And that's the natural way to go from the uniform state to the modulated phase. And that is known as a commensurate-incommensurate transition. Okay, here I give one example where it doesn't matter what the model is. There is a phase diagram parameterized with some parameters. There is a phase here, which I call incommensurate phase number 1. And that phase is sandwiched between a ferromagnet and an L antiferromagnet on a honeycomb lattice. And then what you see is that there is these large domains. If you are close to the L phase, there is these large domains of an L antiferromagnet separated by these domain walls, which are basically ferromagnetic domains. And by moving in this region here, you can go continuously from the L phase to the ferromagnetic phase by changing the relative distance or the relative width of these domains. And the one important thing is that if you draw the evolution of the angle that parameterizes the rotation of the two kinds of sublattices on the honeycomb lattice, there is this Nel regions separated by this kink-like or soliton-like ferromagnetic domain walls. Okay, and then what I said in the previous slide is that you can do numerics, or you can do some simple analytical approximations, and you can predict that the period of the distance between the discommensurations is expected to grow indefinitely as you approach the transition. Okay. Here is another example. It's a very well-known example. This is the three-dimensional version of the K-type antiferromagnet, the so-called beta lithium iridate, which has been known to show this one-dimensional kind of modulation with two counter-rotating sublattices. And similar modulations have been seen in other materials. And there are some numerical investigations that show the relevance of a particular JK gamma model in this kind of geometries. And then there is another theory which says that we can actually describe this modulation as a long wavelength twisting of the closest possible period 3 commensurate state, which is drawn here. And over the last years, we've been able to match the predictions of such a theory with a series of experimental data. Okay, so what about higher dimensional modulations? So there is the picture that if you have inversion symmetric field theories with quadratic spatial derivatives, then there is a theorem by Derrick and Hobart that says that you cannot really get a stable particle-like solution unless we include higher order derivatives. And higher order derivatives are hard to get in condensed matter systems, but instead what you can get in condensed matter systems, which is kind of very standard, is that you can get this chiral or absence of inversion symmetry. And once you have this absence of inversion symmetry, then this kind of linear derivative terms are allowed by symmetry. These are the so-called Lifshitz invariants, and they can go along different directions in space. And the system can accommodate this kind of invariants by forming these localized objects. And there's a lot of examples in the literature from skyrmions, type 2 superconductors to multiferroids and so on. Okay, so here is a skyrmion story that we've been involved with various people over the years on one material that is the so-called copper selenite, which shows this skyrmion crystal phase. And in this system, you have a kind of a distorted pyrofluor with 4 spins in each tetrahedron. So you have in principle 4 vector fields. And the total magnetization, which I call here F, is a kind of a ferrimagnetic order parameter, the primary order parameter in the story, which is drawn here. And then you have these 3 antiferromagnetic counting modes that are possible in this multi-sublattice structure. And then you can derive a long wavelength expansion of the energy, and then you can readily identify the linear derivative terms. So this is one example where such Lifshitz invariants are easy to identify. Okay, here is another example, the Z2 vortices. So this is a triangular lattice antiferromagnet without the K-type coupling, is well known to show this 3 sublattice coplanar ordering. And if we call one sublattice A, the other B, and the other C, and we draw a different color for each spin direction. If we draw the different sublattices in different panels, as done here, you will get basically a sublattice A, all spins pointing in the same direction, sublattice C in 120-degree direction, and sublattice B in this third direction. But what happens is that when you switch this anisotropy, in this case the K-type anisotropy, is that each separate sublattice breaks spontaneously into a super lattice of honeycomb ferromagnetic domains or nearly ferromagnetic domains, pointing along this different, or roughly along this different 4 directions in spin space. And if you look closely, for example, around this region of space where the spins of sublattice A point in the same direction, and as you travel around the core or the center of this domain, all the spins are of the sublattice A point in the same direction. But then what you see is that the sublattice C and the sublattice B spins kind of rotate around the direction of the sublattice A. They do a complete rotation. So what happens, one way to think about this is that in that region, you have, if you draw the ABC local structure of the triangular antiferromagnet, as you go around this center of this honeycomb, that plane rotates by 2 pi, and then this vector chirality basically completes a 2 pi cycle, and then that is known as a Z2 vortex, which has some topological character. It's well known to be a standard excitation of the triangular Heisenberg antiferromagnet. But here, what happens is that as soon as you switch on the K-type coupling, you can condense these excitations in the ground state. And there are some further aspects that I would like to share in this talk. So you can look at energetics. You can draw, let's say, the how much excess energy you have around the centers of these domains or the cores of the Z2 vortices. And what you see is that the cores, of course, cost Heisenberg energy, but give a negative energy contribution from the K-type interactions. You can also do the long wavelength expansion. This is also tractable in this case as well. And what you can see is that in this case, you don't have a vector, you have a rotation matrix, because you have this planar structure, the 120-degree structure, and then you can do a long wavelength expansion, and you can identify the Lifshitz terms coming out from this kind of. If you expand this square, you will get these mixed terms that have one spatial derivative. Okay, so you know that the Lifshitz terms are proportional to the ratio K over J, where J is a Heisberg coupling, and that tells you that in the limit where you go to the Heisberg point, the period or the distance between these discommensurations, or in this case, the topological Z2 vortices, goes to infinity. Okay, one last aspect which is interesting is that if you travel across this cut here, which doesn't go through any of the cores, but in between the cores, then you see that the three different sublattices show kind of almost like harmonic 3Q-like behavior. But if you cut through the cores, you have this soliton-like behavior. And this is a qualitative feature that cannot be captured by any linear approximation. Okay, so far we've been discussing this main paradigm, which is we start with a Heisberg, with a dominant energy part that favors a single order parameter field. And now we switch on a perturbation that favors some kind of twisting of that order parameter field. And in one way or another, the inversion symmetry is broken, and that can generate Lipschitz terms, and you can get interesting modulated phases. But what about if we start from a system that already doesn't have one primary order parameter, but it has multiple order parameters, for example, a highly frustrated system, and then we turn on this chiral perturbation? What happens in that case? Of course, the frustration brings multiple order parameter fields now. That makes it very hard to deal with. You cannot easily do a long wavelength expansion. That's not tractable. You have to resort to some large-scale numerical simulations of some kind of minimization of the energy simulations or semi-analytical approaches. But on general grounds, one expects, let's say, either the simplest case scenario where you basically say the interaction picks one of the competing orders and favors that one, and then it twists it. In which case we end up with something like in the previous case. But then there is the other scenario where you somehow, for different reasons, the frustration may remain robust, and then you can have phases that combine multiple orders. And then you have some kind of a twisting or a combination of these multiple orders. And that's what I'm going to show. The playground is, as I said, the planar checkerboard. This has been a playground for many, many studies over the years as one of the paradigms of frustrated magnetism. I'm going to take Heisenberg interactions, Dzyalozinskii-Moriya interactions. And I'm going to assume that J1, the first neighbor coupling, is the same as the second neighbor coupling, which is kind of unrealistic because in reality, in the plane, these two bonds are symmetry inequivalent, unlike in the three-dimensional paraflow. But nevertheless, I want to stick to this idea that I want a highly frustrated magnet to begin with. So I artificially put J1 equal to J2. I'm going to keep the most general point group symmetry, and that's the C4V point group symmetry with rotations around the centers of these tetrahedra or crossed plaquettes. With the Dzyalozinskii-Moriya interactions that are allowed by this symmetry, then we break the inversion symmetry explicitly. And there are two kinds of DM interactions. One is the in-plane interactions, which are shown here. And then there is also the out-of-plane uniform DM interactions, which we will disregard because they don't break inversion symmetry explicitly and will not give any interesting physics on their own. So we will only keep the in-plane DM components. And the goal is to establish and characterize a classical phase diagram of that model. We have two parameters. We have D1 over J and D2 over J. There is a duality transformation, basically a mirror, the XY mirror plane that maps the phase diagram, the positive D to the negative D part of the phase diagram. So we only need to know what happens in the upper half of the phase diagram. And if you want to ask about relevant materials, of course, there is a lot of materials in the literature, but I think this kind of constraint here is kind of hard to get otherwise. Okay, I'm going to show the results right away. This is the phase diagram as a function of D1, D2. And for comparison, I'm going to show the phase diagram of one single tetrahedron, a four-side problem And as you can see, there is a lot of resemblance between the two phase diagrams, but there is some striking differences. First of all, in the full lattice, I should say almost all phases that we obtain are incommensurate. Some of these incommensurate phases are twisted versions of some special commensurate parent phases, which we are going to identify. And some other phases, like the one shown here, are double twisted versions that combine more than one order parameter fields. And in addition, there is this special line that goes through the middle here. This is the line D2 equals square root of 2D1, around which that line, there seems to be some very interesting things happening. For example, there is many more new phases appearing compared to the single tetrahedron problem. There is a cascade of phases, in fact, if you look closely. And that suggests that there is some kind of a high degree of frustration remaining as we travel along that line. Okay, so let's try to see, before we go into the characterizing these different phases, let's try to get some insights to figure out where this special line comes from, for example, and also introduce some of the concepts. So if you take the model without Dzyalozinskii-Moriya interactions, and you do a Fourier transform and you collect all the interactions into an interaction matrix, and then you diagonalize the interaction matrix, you will get 6 bands because you have 2 spins in the unit cell of the checkerboard, and each spin is a 3-component vector. So you get 6 bands, 3 of which are completely flat, and then there is 3 that are dispersive. Now you can look at these eigenvectors that are flat, the corresponding eigenvectors to the flat eigenvalues. Let's call them V1, V2, V3. All of these eigenvectors satisfy the constraint that the total spin of each tetrahedron must vanish, and that's the constraint that comes from the Heisenberg interaction. That's basically the constraint that leads to all the interesting geometric frustration in the system. And then we can say, okay, what if now we switch on the Dzyalozinskii-Moriya interactions? We can approach this in a kind of a perturbation way. We can take the first order effect of the interaction. It's kind of a degenerate perturbation theory. So we project into this 3 by 3 subspace, and we look at the interaction matrix in that subspace. So if you write down now, if you rewrite the interaction matrix projection into this particular basis, which is what you do when you do perturbation theory, you form the interaction into this amplitude basis, and then you diagonalize. What you will see is that the interaction scales with that combination square root of 2d1 minus d2. And that basically says that that line where that prefactor vanishes, in leading order of the DM interaction, there is no lifting of the degeneracy. So there is some robust frustration along that line to first order in the DM interaction. Okay. Another way to look at this is by going into symmetry analysis, kind of following the spirit of this analysis of these works here. So basically what you have, you take a tetrahedron, you have 4 spins, A1, A2, B1, B2. You form, you put all the components into this 12-member vector, and that provides a 12-dimensional representation of C4V. You can take that representation, you can decompose it into reducible representations of the group, and you find out that you get 1 symmetric irrep, you get 2 times the A2 irrep, you get 2 times the B1 irrep, you get the B2 irrep, and you get 3 different epsilon irreps. The epsilon irrep is the 2-dimensional irrep of the C4V group. Okay, then you can build basis vectors, which are written down here. These are basis vectors for each of these irreps. And then you can also build associated order parameter fields, M fields. And among these 12 fields, we can identify the ones that do not satisfy the constraint that the total spin is 0 in the tetrahedron. And these are basically the fields that do not belong to the manifold of ground states of the Heisenberg point. The rest, 10 IREPs, all belong to that manifold. And then you can take any configuration and you can analyze it into symmetry resolved fields like MI times VI, and you can treat these MIs now as order parameters. Then you can take the Hamiltonian and you can replace in the Hamiltonian, you get an expression in terms of these fields. And you can break down, because this is a corner sharing tetrahedron kind of structure, you can always break down the interactions as the sum over isolated tetrahedral terms, and each tetrahedron energy can be written in terms of the order parameter fields in this particular way. And I have now introduced these combinations, D minus and D plus, which are these combinations of D1 and D2. Okay, so basically whatever comes with a minus sign here, these guys here, these are the fields that I can combine in whatever combination, as long as I satisfy the spinlet constraint to get a ground state of the Heisenberg model. Then there are these terms that are the two IREPs that cost Heisenberg energy. Then there is this term that lifts the degeneracy in first order in D over J, and that's because these terms involve IREPs that are already present in the unperturbed manifold of IREPs here. Unlike these terms here, which always combine a coupling between IREPs of the unperturbed manifold and IREPs that cost energy. These kind of terms, they mix in these intruder IREPs in second order perturbation theory. So they will have an effect only in second order in D plus over J. So that means that if I draw now this phase diagram, I draw these two lines, I know that along this line here, when D plus is 0, along this line where D minus is 0, I'm sure to get a second order effect only. I will not get a first order lifting of the degeneracy. So in that sense, again, I find the same thing, that along this special line, I do not lift the degeneracy to leading order. Okay, so let's go back to the single tetrahedron problem. We can identify now these phases with different IREPs. So this is the IREP B1A that satisfies the total spin is 0. This is one of the ground states of the Heisenberg model as well. This is the dual of that phase. And then there is this phase in between, and that phase is, you can think of this as a canted all-in or canted all-out state. That phase couples two IREPs, one the A2A that belongs to the unperturbed manifold, and the other the A2B that does not belong to the unperturbed manifold. And this phase combines the two fields in this particular way, where the angle phi is proportional to the ratio D plus over 2J. So the more I move along this line away from the origin, the more I include canting. So basically the canting is introduced by this mixing of this intruder IREP here. So that's the only phase of the single tetrahedron problem that does not satisfy, that does not belong to the amplitude manifold of the Heisenberg model. And that phase is basically generated by one of these cross-coupling terms that I showed in the previous slide that combines the coupling between 2A and 2B. Okay, and again, this is the axis D plus and this D minus. So the more I move along this line, the more I favor this term becomes more and more relevant, and that's why I generate this phase. Okay, now we go to the full lattice phase diagram. Let's start with this configuration here. That's an incommensurate configuration. We have identified the parent phase of that configuration, and that parent phase lives along this line here. So along this line, we have identified a period forced orthogonal configuration, which is also coplanar. It's actually a one-parameter family of ground states of that sort. The order wave vector is is period 4, so it's pi half along the diagonal of the lattice. And that configuration is not just B1A for the single tetrahedron case, but now it combines A1, B1, B, and one of the epsilon configurations as well. And just for the parent phase, you can easily see that the total spin in each tetrahedron is 0. Okay, now if I show the twisted version of that, it has a depending on the value of the DM interaction, it can have varying period. So here I'm showing one of the states that has a very long period, and you can move along different. You can show different projections. If you look at this particular projection here, which is this direction here is the propagation direction, the x minus y. You can clearly see the two kinds of sublattices co-rotating in a fashion that resembles very closely locally the orthogonal configuration. So the wavelength is not precisely 4, is actually a very long wavelength, but locally it approximates the period 4 state. The two sublattices, if you draw a common origin plot of the two sublattices, you will see that each sublattice has an almost coplanar helix configuration, but then there is an angle between the two spin planes. And the angle between the planes goes to 0 when we approach the parent phase, because the parent phase, as we said, is a fully coplanar state. And if you Fourier transform, as I said, is very close. The Bragg points are very close to pi half. If you draw how the angle of rotation in the spin plane evolves as a function of distance as I travel along the propagation direction, and that's the black line here. You can identify some kind of weakly nonlinear aspect, some kinks, and this other line here is so-called the linear approximation to, or linear ansatz approximation to that phase. And what happens is that kinks become more and more pronounced as we go to the parent phase. But as it turns out, you have to go to very, very tiny numbers in order to see some serious kinks. So I should say this phase is very well approximated with a linear or perfect helix kind of configuration, almost in the entire phase diagram of the stability region of that phase. Another aspect of this phase is that that the period or the optimal wavelength of this configuration diverges as we approach the parent phase when D2 goes to 0. And these periods here have been obtained in different ways. So numerically, what we do, we can do a brute force minimization algorithm. This turns out to be very hard because we do single spin updates, and when you reach such large system sizes, it's very hard to get some sensible results above these sizes. But then you can do more clever kind of initial approximations where you use some kind of variational ansatz as initial states, and then update those configurations in the computer and get some better results. So this is what comes out of these calculations. We have tried different cluster sizes, and then we plot the energy versus the cluster size, and then we choose the optimal cluster size that fits the configuration. And this is basically the plot that comes out from this analysis. Okay, now we move on to this phase, which is a so-called twisted all-in all-out phase, or P1X phase shown here. We have identified the parent of that phase as the one being one of the members of the Heisenberg model ground states manifold. And that particular member is this all-in, all-out configuration, which has ordering wave vector pi. And as it turns out, you can tile this configuration as long as the DM interaction is 0. But as soon as you switch on a DM interaction, the picture I showed earlier is that the all-in configuration actually favors positive canting, whereas the all-out configuration favors a negative canting. So if you have a non-zero Dzyalozinskii-Moriya interaction, as you move along this line and go into the phase, you generate some canting, which is frustrated. It cannot be positive, negative, positive, negative as you go all in, all out, all in, all out. That generates some frustration, which leads to some incommensurate twisting of the canting, in fact. And this is in more detail what I've been describing. You can
Ioannis, if you can wrap up in a couple of minutes, that would be great.
Yeah, I actually have just this slide and the next, and that's it. Thank you. As you go along the propagation direction, you can locally identify the all-in, all-out structure, but then you can also draw the total spin in each of the crossed tetrahedra or cross plaquettes here. And you can see that there is a very slow rotation in the x minus y z plane, which you can also see in this projection here. If you do the common origin plot, you will see this kind of butterfly structure. And you will also see this kind of jumps in the evolution of the angle. There is these sudden jumps. You can also identify these sudden jumps in the evolution of the order parameter fields, and also more explicitly in this angle. Looking again at the red line here, the blue is the linear approximation. There's this clear jumps, and these kind of jumps become more and more pronounced as we go towards the parent phase. Okay, so that phase is one of the richest phases that we have seen, with a butterfly-like structure and clear evidence of kinks that become more and more pronounced as we approach the parent phase. Okay, and now final slide is basically the extra phases that we see sandwiched between what I already discussed. There is this very large region, which is called P11 here. There is this blue region, which is called P31. There is some other narrow regions in between, which is P11 plus P31. And then there is also this other phase up there. Okay, so what are these phases? I'm only showing two panels here, representative ones. One is for this large phase and the other is for this blue phase. What we see here basically is that we see a double twisted modulation. We see a modulation along the direction that we had before, but now we see also a modulation in this direction. And the best way to think about this is that you have patches or domains of all in, all out kind of state separated by JD1 twisted kind of state. So it's basically a combination of the neighboring phases, what we get in between. And the relative widths of these two domains. So here we see the width here is 1 for that domain. And in this phase, the width of the JD1 part of that configuration is 3 versus 1. And possibly there is other states in an even narrower regions sandwiched in between. But these are required very large system sizes to check. And I'm saying this because the natural way to think about this phase is that you go again from one phase to the, let's say you want to go from this purple phase to the green phase, and you have this red phase in between. So you combine domains of the purple and domains of the green. So the natural way to go about this is to first do a commensurate transition here, where the period of these commensurations of this phase is infinitely large, and then you decrease the period and so on. But that does not seem to happen in this case. What we see some 1 or 2 phases in total. We cannot find other phases with longer periods, or we cannot check otherwise numerically. Okay, so that concludes basically the story that is in preparation. So basically the idea is that, beyond the traditional paradigm, can we get more interesting phases by using this idea that we can now combine more than one order parameter fields in addition to the and the Lifshitz invariants, which were very hard to track down in this kind of problems anyway. Thank you very much for your attention.
Thank you, Ioannis. Do we have any questions from the in-house participants?
Ioannis, thanks for a nice talk. I have a very short question. You have in your phase diagram many places where there is continuous degeneracy. And is there a possibility of selection by disorder operating here? Like if you introduce thermal fluctuations, it selects certain configurations. So will it, I mean, it should be working here also.
Yes, so you are referring to, so I should say there is only very special lines in this parameter phase diagram that you have this, let's say, accidental degeneracy. Yeah. Otherwise, you have the explicit order by disorder. So as soon as you put it, let's say, in this example here, as soon as you put a D2 interaction, you lift the degeneracy explicitly. I suppose if you sit on this line, let's say in a material that doesn't have D2 interactions, and you heat up the system, then such a scenario can happen. Although I should say probably not in this particular case, because here the degeneracy is actually symmetry related.
I see.
So you have this translation that you have you have this angle phi, which is basically where you put your origin of rotation, and then on top of that you have this translation. So I think that angle will be selected spontaneously.
Yeah, okay, we can discuss it later.
Yeah, sure.
Is there any more question? If there is a question online, you can unmute yourself and ask. Okay, I think that's not the case, so we can move on to the next talk, but let's thank the speaker first.
Thank you. All the best.